So this lesson is going to wrap up everything that we've done as far as curve sketching goes. First derivative test, maxima, min, extrema, concavity, second derivative test. Going to have some intercepts, talk about some symmetry, domain and range, some asymptotes. Just kind of put it all together into one ginormous problem. They can get lots of good multiple choice questions from these kinds of problems. So pieces of these mammoth problems are great multiple choice, but then one big one is also a fantastic free response question or an FRQ. Okay, so all of these questions, I think there are 6 of them. For the notes, I'm going to be asking you the same thing, to describe in detail and to sketch the curve. You're welcome to use a calculator to check your answer, but I need all of this information in massive detail. So I want the x-intercepts and the y-intercepts. So to find that, to find the x-intercept, you're going to plug 0 in for y and solve it. And I only want those if it comes out pretty. The y-intercepts, you're going to plug 0 in for all the x's. So if you want to make a little note, x-intercepts, you're going to plug a 0 in for y, and the y-intercepts, you're going to plug a 0 in for x. Symmetry, domain and range, continuity, obviously, is always something we have to check for. Asymptotes, just to refresh your memory, to find vertical asymptotes, that's you set the bottom equal to 0 and solve it. Horizontal asymptotes, you have to worry about the degrees. If the degree of the top is bigger, there are none. If the degree of the top is equal to the degree of the bottom, it's y equals a over b. A is the leading coefficient of the top, b is the leading coefficient of the bottom. And if the bottom degree is bigger, then it's y equals 0. So all of that's from like Math 3 and pre-cal. Slant asymptotes is from pre-cal. If the top degree is bigger than the bottom by 1, then you divide the bottom into the top. Hopefully with synthetic division, sometimes you have to use long division. And whatever you get when you divide, and you completely ignore the remainder, but whatever you get when you divide is y equals mx plus b, and that's your slant asymptote. There is one problem in the homework that has a slant, so you need to make sure you're good with that. And you've always got your pre-cal notebook. You can go back and find those and look for that. Differentiability, if you can take the derivative, that's your sharp turns. And if it stops increasing and decreasing, that's your first derivative test. Relative extrema is from the increasing and decreasing. Concavity is your second derivative test. And your limits as you approach infinity, that's after it's done doing all its wiggling. In the long run, to the right and to the left, where is it headed? Okay, so all of these pieces of information we're going to do for every single problem. Now the notes you have are completely filled in, so that's how I'm going to teach it. We're just going to walk through the information, but I wanted you to have the words that went behind the notes, so you can kind of follow along. Okay, so here we go. Number 1 says analyze and sketch the graph, and that's it. Those are the only directions we have. So you have to know that you need all these pieces of information. Okay, so for number 1, he's cubic. So I know he's continuous and differentiable. So I state that. B, we're going to do the intercepts. So the x-intercepts, I'll plug a 0 in for my y. It doesn't factor. I could go graph it and get decimally stuff, but if it doesn't factor, if it doesn't come easily, then don't worry about it. I know that sounds weird, but you don't have to worry about it. The y-intercept, you're going to plug a 0 in for all your x's, which is super easy, and you're going to get a 7, but make sure you write that as a point, 0, 7. So that's my y-intercept. Okay. Part C, I need my critical points, my increasing, my decreasing, and my maxes and my mins. I get nothing from f of x, like he has no asymptotes, he doesn't stop, like there's nothing weird about him, so I get no critical values from him. So I take the derivative, and I set it equal to 0, and I factored it, and I solved it. So these become my critical points, so they help me set my interval. So I'm going negative infinity to negative 1, and then negative 1 to a 1/3, and then 1/3 to infinity. I pick numbers in those intervals, and I plug it into my derivative to figure out if I'm positive or negative. I'm going to plug it back in here and just see if that turns out to be positive or negative. Again, I don't care about numbers. I just want to know the sign of my answer. Okay, so once I've done that, then I know that I am increasing on those two intervals, and I'm decreasing on that interval right here. So I've got that boxed in. So then I know that if I'm increasing and then decreasing, I know that right here it's going to be a relative max. So it's going to happen at -1. And that this is decreasing and then increasing. So I know at 1/3 I'm going to have a relative min. Then to get their y values, I plug it back into the original function. So I'm finding f of -1 and f of a 1/3. Always stick with fractions if you can. I went decimal kind of off here to the side because I am going to have to graph it here in a little bit. Okay. So then I'm going to come to part D, and I'm going to do concavity and inflection point. So concavity, I take the second derivative, I set it equal to 0, and I solve it. And that helps me define my interval. For my concavity test, I pick numbers in those intervals and plug them into the second derivative. So I'm plugging them back into here. Okay, so I can tell that I'm concave down in this interval and concave up in this interval. I also know because my concavity changes that I have an inflection point at -1/3. I need to find f of -1/3, and I get 200/27, which is about 7.4. End behavior, I know from pre-cal, since he's an odd degree, that he will begin and end in opposite directions, and since his leading coefficient is positive, I know he will rise to the right. And because he's odd, I know he'll do the opposite to the left, so he will fall. Then that's it. That's all the information I need to draw my graph. So I'm going to put my max and my min on here. So I've got these 2 points. I'm going to put my y-intercept in here. So he's there. And then my max and my min. And then I know that as I head to infinity, I'm rising. And as I head to -infinity, I'm falling. And then I just draw my little humps. And again, I never found the x-intercept. It's somewhere down here somewhere. But because it was ugly, we didn't have to go find it. All right. So there's one problem, start to finish. Now, he is very nice. He doesn't have any asymptotes, like there are no hiccups here, like it's just a very nice, well-behaved function. So this was just to get you comfortable with all the things that you have to find. Okay, so number dose, again, he's cubic, so this is another nice guy, so we're going to enjoy this while we have it. He's cubic, so he's continuous and differentiable. That's not a problem. Intercepts, I can actually find these. For the x-intercept, I'm going to plug 0 in for y. Then I GCF'd an x, set both those equal to 0, and solved it. So this one I got a 0. This one, if I take x squared and I add the 12 over and root both sides, I'm getting ±2√3. Again, write them as points. For the y-intercept, I plugged a 0 in for all my x's, so I'm going to get a 0, so he's going to be 0, 0. So intercepts were easy. Critical points, increasing, decreasing, maxes, and mins. Again, I had a very well-behaved original function, so I didn't get anything from him. I take the first derivative. I'm going to GCF a 3 just to make life easier, and then add 4 and root both sides. I'm going to get a ±2. So those become my critical points. I set my interval. I pick numbers in those intervals, plug it back into the derivative. So I'm probably going to go there without the 3, and plug it in and see if I'm positive or negative, and then I can state whether I'm increasing or decreasing. Then I know because I'm increasing and then decreasing, I know I'm going to have a max at -2. And this is decreasing and then increasing, so I know I'm going to have a min at 2, and then I just do find the function's value at those 2 x's, and that gives me the y value. So that's my relative max, my relative min. Okay, then I come up here and do my concavity, my inflection point. So I take the second derivative, set it equal to 0, and solve it. I get a 0. So that makes very nice two little intervals. I pick numbers in between those intervals, and then I plug them into the second derivative. So I can do my concavity. I'm going to be concave up here and concave down here. Because my concavity changes, I do have an inflection point. I do have to find his y value, so I have to find f of 0. Plug that into the original function, I get a 0. Inflection point is where the concavity changes. End behavior, again, because he is a positive leading coefficient, he will rise to the right. And because he is an odd degree, he will do the opposite to the left. And again, I come in here and I put my relative maxes and my mins on my graphs. And I think I went up by 2s. And then I put my intercepts in here. I just went in there and found what decimals those were from here. And then I knew that I'm rising to the right and falling to the left, so I can draw my cubic function. And again, you're welcome to graph this on your calculator to double check yourself when it's all said and done. That's totally fine. But also know that on the AP Calculus exam, you have multiple choice with a calculator and multiple choice without. And then you also have FRQs, free response, with a calculator and without. Okay, now number 3. Okay, so we're dipping our toes into a little bit of a not well-behaved function. He is not continuous because he has asymptotes. Okay, so first I set the bottom equal to 0 and solve it. I know that he's going to have a vertical asymptote. You cannot write vertical asymptote plus or minus 2. Vertical asymptote is a vertical line, so it has to be x equals plus or minus 2. Horizontal asymptote, the bottom degree is bigger, so that's y equals 0, and that's just remembering those rules from pre-cal. This is completely differentiable except at the asymptotes, but it is differentiable, so you can put a check there as long as you address the fact that it has asymptotes. Intercepts, I plug a 0 in for my y. So when I'm right here and I'll multiply both sides by x squared minus 4, that's going to completely cancel and leave me with 3 equals 0. So I have no x-intercepts. Y-intercept, I plug a 0 in for my x's, and I get my point. Critical points. Now, remember, you have x equals plus or minus 2 from the original function. So that is where you are discontinuous. So those are 2 of your critical points. So then I take the first derivative, a little low-d high, high-d low over low-low, clean it up, then set this equal to 0, multiply both sides by the bottom, so the bottom's going to go away, and then divide by -6, so I get x equals 0. So I have to take these from the asymptotes from the original function, and this, which is from taking the derivative and setting it equal to 0, and all 3 of those become these critical points. So I've got to hop over -2 and hop over 0 and hop over 2. So then I pick numbers in each of those intervals. And then this right here, that's just me plugging it into that and figuring out the sign of the top and the sign of the bottom. So that's going to be positive over positive. This one's positive over positive. The next one's negative over positive. So I know he'll be negative. And again, so I know that I'm increasing from negative infinity to -2, and then from 2 to infinity. Hold on. Okay, so I missed a little negative right here. He should be negative. I wish I could get it. Okay. He should be negative because, let's go back and look. We are increasing, but I can't be increasing from negative infinity all the way to 0 because I have an asymptote at -2. So in my interval, I'm increasing from negative infinity to -2 and from -2 to 0. Do not write that as one big interval because you have an asymptote smack dab in the middle of it. Okay, so you have to write that as 2 separate intervals. Notice that those are parentheses on that -2, which means we don't include it. And then I'm going to be decreasing from 0 to 2 and 2 to infinity. Again, I cannot write this as one big interval because I have a big old asymptote right here at 2. Let's see, and then our increasing and decreasing change right here at 0. So I do f of 0 and figure out that his y value is a negative 3/4. Now that's going to be a relative max because I'm increasing and then decreasing. No max or min at 2 or at negative 2 because those are asymptotes. And that's also, the increasing and decreasing does not change. Okay. So now we go up here to concavity and inflection point. So now I have to take the second derivative. So I'm going to take my first derivative, which is boxed right here. And I go second derivative on him. And that's just some good old algebra. Watch your signs. Be super careful. There's a couple chain rules in here. I get it down to this. Set that equal to 0. Multiply both sides by the bottom. Bottom's going to cancel. So then I subtract my 24. Divide by 18. That's going to be a negative. Then I root both sides, and I can't root a negative. So I get no solutions from him. But what I can still use are the asymptotes from the original problem. So I still have my break at negative 2 and my break at 2, even though he didn't give me anything. I pick my points, I plug them into my second derivative, and this is me doing sine over sine to figure out what the sine of the final answer is going to be. So then I know that I'm concave up in this interval and this one. And concave down in this interval in the middle. I have no inflection points, even though my concavity changes, but there are no inflection points since the change happens at an asymptote. And they really do want you to specify that because that's normally where you would list what your inflection points are. It's not a polynomial, so you don't have to look at end behavior, which is really, really nice. Polynomial was going to be something that looks like number 1 or number 2. This one is called a rational function because it's a fraction with x's top and bottom. So you don't have to worry about end behavior. All you have to do is state not a polynomial. You know you've got your asymptotes. You know you've got your increasing and decreasing. You use your concavity. You do have one y-intercept. You can see why you don't have any x-intercepts because you have an asymptote on the x-axis. You can use your calculator to help graph this, but I want to warn you, you need to be able to graph this just based on the information that you have discovered. Because sometimes you'll be asked to graph this without a calculator. But with the increasing, decreasing, and the concavity and your intercepts, you should be able to graph this without a calculator. Okay, number 4 is another rational function. You're not continuous because we got some asymptotes going on here. So we state no, and then we say we've got a vertical asymptote. We set the bottom equal to 0. That's going to be x equals negative 2. Horizontal asymptote, the degree of the top is a 1 and the degree of the bottom is a 1. So they're the same. So it's y equals a over b. A is the leading coefficient of the top. B is the leading coefficient of the bottom. So that's going to be y equals 3. Differentiable, absolutely, except at the asymptotes, and you're fine as long as you state that. Intercepts, I'll plug 0 in for y. Multiply both sides by x plus 2. Divide by 3. Get x equals 0. So I have an x-intercept at 0, 0. For the y-intercepts, I'll plug 0 in for my x's. And I get 0 over 2, which is 0. So I have a y-intercept at 0, 0, which makes sense. If you have an x-intercept at 0, 0, you're also going to have a y-intercept at 0, 0. Critical point, so I know that I have my x minus 2 from my original problem. So go ahead and state him right up front. That's just from the original function misbehaving. So then I find my derivative, and then I set it equal to 0. And my x's completely go away, so I get no solutions from him. But I still have this guy from my asymptotes. So that becomes my critical point, my only critical point. I pick values in those intervals, plug it into my derivative, and see what my signs come out to be. And I can see that I'm increasing the whole time. But I can't write it from a negative infinity to a positive infinity because I have an asymptote at negative 2. So I have to write it as 2 separate intervals because I have to state that I'm crossing over an asymptote. Because he's increasing the entire time, I have no max and no min, and you need to make sure that you state that, address it. So then I do concavity and inflection points. So I'm taking the second derivative, little low d high, and then set that equal to 0, and the x's completely go away. I get negative 12 equals 0, so I get no solutions from there, but I do have an inflection point because of the asymptote. So again, I pick numbers in those intervals, plug it into my second derivative, which is right there, figure out what my signs are going to be, and I can see that I'm going to be concave up from negative infinity to negative 2 and concave down from negative 2 to infinity. I do not have an inflection point at negative 2 because it's an asymptote. For part E, it's not a polynomial, so you don't have to worry about end behavior. You put your, well, I missed my intercepts, sorry. This guy should do more like that because I had an intercept at 0, 0. So you can see that this graph is increasing. It is rising, and it is rising. So it's increasing for its entire life. It's concave up from negative infinity to negative 2, and it's concave down from negative 2 to positive infinity. So again, make sure that your graph kind of jihas with everything that you found out. Okay, so those were cute little misbehaving problems that had asymptotes. This guy is a little different because he has a root. If you think about that x to the 2/3 as a cubed root. He is not a rational function, so he has no asymptotes because he's not a fraction, doesn't have any x's on the bottom. So he is completely continuous. He is not differentiable. He has a sharp turn at x equals 0. I don't expect you to know that off the top of your head. I don't think they would expect you to know that either, but you would need to graph him. Any graph that doesn't have a parent function of something you're familiar with, x squared, absolute value of x, x cubed, x to the 4th, a rational function. This, we don't know the cube root of x squared. That's not one of those functions that we just know. So you graph him on your calculator and go ahead and hit pause and graph him on your calculator and see that he has a sharp turn at x equals 0. So you know he's not differentiable there. Okay. Now we're going to find our intercept, so we're going to plug 0 in for y. I'm going to subtract my 2 and then divide by the negative, so it all turns out to be positive. And then to get rid of the cube root, I'm going to cube both sides. That's where the 8 comes from. And then I square root both sides, and that's where the plus or minus 2 root 2 comes from. Okay, so those are my intercepts. And then the y-intercept, I'm going to plug 0 in for x, which is really easy and gives me 0, 2. All right, my critical points and my increasing and decreasing. Remember, you have a sharp turn at x equals 0. They call it a cusp, and you can see from the graph, that's what they call a cusp, which we haven't dealt with very much. And doesn't pop up that often, but you know, it does pop up enough to where you need to know what that is. I'm going to do the first derivative, and then I'm going to clean it up and put my cube root of x on the bottom, set that equal to 0. And when I solve it, my x's completely goes away. But remember, we had a sharp turn at x equals 0, and my first derivative is also undefined at x equals 0. So 0 becomes one of my critical points. I pick numbers in both those intervals, test them in f prime, which is right there, and figure out what my signs are going to be so that I know I'm increasing from negative infinity to 0 and decreasing from 0 to infinity. I do have a max at 0 or a max or a min. I have to figure that out. But something does happen at 0 because that's not an asymptote. Like that point is defined on this graph. So that is a max or a min. I'm increasing and then decreasing, so I know it's a max. And then to get the 2, I just find f of 0 of the original function. Okay, so now I'm going to take this guy and I'm going to go find his derivative. So I'm finding the second derivative. I'm going to rewrite it, put that stuff on the bottom, set it equal to 0, and solve it. All my x's go away, but again, weird stuff is happening at 0. So 0 is going to be one of my potential inflection points. So I go from negative infinity to 0 and from 0 to infinity. I pick points in those intervals and plug them into the second derivative. So I'm plugging them in here. Everything is being raised. Anything I plug into x is being raised to the 4th power, so I know it's all going to come out to be positive. It's always going to be positive on top, and this is always going to turn out to be positive. So I'm concave up for the whole thing. And again, I don't have to break it at 0 because that's not an asymptote like it was before in number 3 and number 4. But I have no inflection points. You need to make sure you stay that because my concavity doesn't change. This is a polynomial, so you can do right and left behavior. Your leading coefficient is a -1, so to the right you're going to fall. This is an even power because it's being squared, so whatever it does to the right, it's going to do to the left also. So it will fall. I've got my asymptote, or not my asymptotes, my intercepts on here from what I found in part B. I've got my increasing and concave up, so increasing and then decreasing and concave up and concave down. And there's my sharp turn. It is also not just a relative max, it's also an absolute max because the function never gets higher than that. Okay, last one, number 6. He's kind of a play on a rational function, but the whole thing is being squared. So he's a little bit more fun. We're not continuous because we know we're going to have a vertical asymptote at x equals -3. I'm going to have a horizontal asymptote at y equals 1 because the degree of the top is the same as the degree of the bottom. They're both x squareds, by the way. So I take the leading coefficient of the top, which is a 1, and the bottom, which is a 1. So it's y equals 1 over 1, which is 1. I'm differentiable, absolutely, except at the asymptote, which I have addressed. Intercepts, I'm going to plug 0 in for my y, just what I've done here. Then I'm going to square root both sides to get rid of the square, and then I'm going to multiply both sides by x plus 3. And that's going to give me 0 and add 4. Very easy. And then I'm going to plug 0 in for my x's and get -4 over 3, but then I'm going to square it and get 16 over 9. So 0 and then 16/9. And I'm going to go ahead and figure out what that is as a decimal because I know I'm going to have to graph it. Okay, critical points, increasing, decreasing, max, and min. So I know I have issues at x equals -3. That's just because he has an asymptote. To do the derivative, I did a power rule with a chain rule in it. So I pulled the 2 down, knocked 1 off my power, and then I took the derivative of the inside. And then the rest of it is just cleaning. So take your time and walk through that and make sure you're good with the math part of that. Cleaned up, then set him equal to 0. The bottom's going to go away. And then here I just divided by -14, so it went away and then added 4, and I got x equals 4. But remember, you have x equals -3 from the original functions where he misbehaves. So I've got stuff happening at -3 and at 4. Those are my critical values. Pick numbers in those intervals, plug them into my derivative. And again, this is me just plugging it right in here and figuring out what the signs are going to be. So now I'm increasing from 0 to -3 and from 4 to infinity. And I'm decreasing from -3 to 4. I have an asymptote at -3, so that can't be a max or a min right here at -3. But something can happen at 4 because he's not an asymptote. If that's decreasing and then increasing, then I know that's going to be a relative min. And then I just find f of 4, and that turns out to be 0. Okay, concavity. So now I'm going to take the second derivative. So I want you to take your time and walk through that because there's some really good math in there. So feel free to hit pause and just walk through the math for how to take the second derivative and the cleaning up. Okay, once you're done, you're here. Set him equal to 0, so the bottom's going to go away. Subtract 210 and then divide by -28, so I get 15 over 2. But again, remember you have an asymptote from the original function. He gets included in your inflection points or potential inflection points. So I have a cutoff at -3 and a cutoff at 15/2. So I fix my intervals, pick numbers, plug them back into my second derivative. So I know I'm concave up from here to here because they're both positive, but because that's an asymptote, I have to do it as two separate intervals. And then I'm concave down from here to here. This can't be an inflection point because it's an asymptote, and I stated that, so put your Captain Obvious hat on and state that. And then I'm going to have an inflection point at 15/2. This is me finding f of 15/2. Make sure you can do that. And then I graph. It's a little bumpy, but you know, what's going on here? Okay, so I've got a Y-intercept here, an X-intercept here. All that is from part B, I think it is. I've got my asymptote at -3, and I've got my inflection point. Remember, inflection point is where concavity changes. So I know on this interval I'm increasing and concave up. On this interval I'm decreasing and concave down all the way to here. Then this is where my decreasing stops and my increasing starts, but I'm still concave up. But then right here is where I'm still increasing, but my concavity changes to concave down. And that's how I don't ever cross that asymptote up there. So again, take your time. Really make sure you're good with all the math. I mean, the overall umbrella process, absolutely. But the nitty-gritty math, make sure you're good there too. And, you know, practicing in the homework. And I didn't give you tons of these because they are so involved and so in-depth. I think you have 7, but the first couple are super, super well behaved. So it's a nice way to kind of get your feet wet. And then they get a little bit more fun after that. And I think even I wrote some notes on some of the answers that are posted about what to watch out for and which ones are a great problem. So just make sure that you take your time and give it the attention that it deserves.